Hi guys, welcome. Hope you guys are getting settled into doing your online learning. Everyone's safe at home, getting ready to do a bunch of learning for the last quarter through these little videos. All right, so before the break, higher level, we're just about finished higher level gravity. We all pretty well finished all the concepts, but what I wanted to do is make a few more videos just to remind us a few things. I know it was a bit hectic for that last week and a half, and there's a lot of other stuff on our minds, so maybe we didn't do the best job going through all this stuff. You guys had a good problem set. Hopefully you've done all 10 problems on those problem sets, and you would have come across some of these questions that we're about to do, or these concepts we're about to do in these next two videos. So this video is about orbital motion, stuff that we've already done in circular motion, but adding a little bit more complexity since it's higher level. Okay, the two objectives that we're going to cover in this video is deriving an expression for orbital speed. So if I'm at any position in a gravitational field, I should be able to calculate what velocity I need in order to be able to maintain that orbit. And the last thing that we'll do, which is what we did in class, is creating an expression to calculate the total energy of an object in orbit, and just discuss what is it that we can do with that knowledge. How can we use total energy to calculate certain things? Okay, so from our previous circular motion unit, we've seen this picture before. You've seen the moon orbiting, or a satellite orbiting the Earth, and we talked a lot about this relationship that you see on the right-hand side. So something that was on Lewis's problem was the term tangential velocity, and I want you guys really to get used to that. When an object is experiencing tangential velocity, okay, when it's in circular motion, a tangent, like in a graph, is a slope that is touching that graph. Okay, so that's what the moon is doing. You can imagine that circle is the graph of the motion, and the velocity would be tangent to that circle. So the velocity is perpendicular to that centripetal acceleration that's pointed to the Earth. For an object to experience circular motion, it has to have a tangential velocity. The velocity always has to be perpendicular to the force pulling it towards the center. Okay, and that's what makes objects go into a circle. So the term tangential velocity just means what velocity does an object have if it's experiencing circular motion, that v in the mv squared over r. Okay, so for the moon to experience circular motion, it experiences a force of gravity that's pulling it towards the Earth, but it has a tangential velocity to keep it in orbit. If it wasn't there, the moon would come crashing into the Earth. Okay, the relationship is mv squared over r is equal to g me m over r squared. That's Newton's universal law of gravitation, and that's centripetal force, or one version of it. Okay, now from that, if I wanted to calculate what velocity I need for the moon to maintain that orbit, I can create some pretty interesting expressions. Okay, I'm going to look at the right-hand expression over here. If I do some interesting cancellations where if I go and cancel the mass of the moon, okay, and I just follow this expression downwards, you'll see we come up to some familiar stuff. Okay, so for example, v squared over r is my centripetal acceleration, and gme over r squared is gravitational field strength. So we've come up with an interesting relationship that if I want to calculate the velocity of an object at a certain point, if I know the gravitational field strength at that point, that gravitational field strength is my centripetal acceleration, and then I can work backwards to figure out many things, such as the velocity of that object or the period of its rotation, knowing its centripetal acceleration. You have formulas in your data booklet that would allow you to calculate the period, for example. So I'm not going to put that in here. Okay, now the relationship on the left is what Lewis did in his problem and what I did in my solutions. Okay, to calculate the velocity needed of the moon, all I'd have to do is calculate cancel the variables that would cancel on either side, so r and that leads me to that expression, which is v squared is equal to g me over r. This looks familiar. That's gravitational potential. So the velocity that I would need would be the square root of my gravitational potential, as shown in that box over there. So something that I want you guys to get familiar with in higher level is that we can create a lot of interesting expressions from formulas and equations. And using those expressions, we can then substitute them into other expressions to calculate variables. And using systems of equations, that's a common theme in higher level, that we have to be comfortable doing that. Okay, and so something I was talking about throughout our lessons on higher level gravity is becoming, I don't know, familiar with the concept of being like a DJ of physics, where you can create expressions that you can then substitute into other ones to solve something that would be relatively unknown. Okay, and that's what the big picture is behind this unit. Okay, another thing I presented is total energy of orbiting systems. Why do we need to know about the total energy of a system? Well, just like in the mechanics unit, I can solve how high I throw a ball if I know the kinematics variables. I can also solve how high I throw the ball if I know how much force I put on it. Then I can use Newton's laws and then get the kinematics variables. And something at the end of the mechanics unit was using the idea of conservation of energy. Okay? And that gave us relatively simpler methods to solving problems. Knowing the work and then using kinetic energy and potential energy often gives us a simpler, more direct way of solving problems. So we can go back and solve what is the velocity of an orbiting system. If I knew the total energy of that orbiting system, I might be able to come up with a relatively quick way of doing that. So we're going to look at that. All right. So why are people interested in it? Well, in reality, for NASA, if I want to figure out how fast I have to send out a satellite so it orbits something like the moon or Jupiter, I'm really thinking about the total energy of the system, and I'd have to change that total energy of the system in order for it to change orbits. And so I'm going to post a few videos online that I liked, that I've been watching this week, that talk about just everything you would need to know in order to launch a satellite from Earth and place it at orbit, or to take a satellite and move it somewhere else. That's a little bit more complicated than what we're doing, but it's good for you to see the application of what we're doing. All right, so this is really important. How to calculate the total energy of orbiting systems. We have to be able to remember how to derive this equation. So I would take some special note. Make sure you put it on a cue card because it often appears, okay? So the total energy of any system is going to be equal to the kinetic energy plus the potential energy. We know that. And in this case, the total energy is going to be 1/2 mv squared, which is the kinetic energy of an orbiting object, plus the gravitational potential energy, which is written by this formula over here. And remember, the gravitational potential energy is negative. All right, we derived that before. So if I knew the velocity of the object and I knew the distance, I can calculate the total energy. But I'm going to show you something else. I can also calculate the total energy without even knowing the velocity. Just knowing the radius and the mass of the object, that's all I would need to know in order to be able to calculate the total energy. And it's a pretty cool derivation. So in order to do this, you see this box around mv squared. I've seen that before in a formula up top. So I'm going to show you how I can DJ my way into getting a new relationship. So if I go up to the top over here, you'll see the centripetal force and the force of gravity equality. If I'm just going to copy this and move it down. Okay, so if I take that relationship and just paste it over here, okay, you'll be able to see. I'm just going to erase this, write it out better. Okay, I can see that there's an mv squared in this formula over here. And if I rearrange the formulas, I can substitute that mv squared back into over here. So I can simplify these formulas by getting the r's out. So mv squared is equal to g MEM over r. So for that mv squared over here, I can take this and substitute it in. And what that will leave me is 1/2 g MEM over r is equal to negative g MEM. Oops, sorry, not equal. Okay, plus negative g MEM over r. Okay, and then I can combine those terms and I'll be left with negative 1/2 g MEM over r. Okay, so that means that the total energy of an orbiting system is equal to negative 1/2 g MEM over r. All I would need to know is the radius of that object, and I'd be able to calculate the total energy. Something else that's pretty cool is that 1/2 g MEM over r is equal to my kinetic energy. So something new pops up, that the total energy of a system that's orbiting is equal to negative 1/2 g MEM over r, and the total energy is equal to negative kinetic energy, because 1/2 g MEM over r is equal to kinetic energy according to that relationship that we created. Now that's pretty cool. Okay, so the total energy of an orbiting system is going to be equal to the inverse, or the negative, of the kinetic energy. And we can see that in this graph over here. If you take a look at the kinetic energy of that orbiting object, okay, it's positive. It gets larger as we get closer to the surface of the planet. It gets smaller as we move away, just as we'd predict. And the total energy would be the negative of that value, okay? Now, potential energy is much larger and more negative, and as we get further and further away, infinite away, the potential energy is going to become zero. So if you subtract the potential energy, or actually you add the potential energy to the kinetic energy, you'll get the total energy as we derived in the relationship below. And then from that table, NASA scientists would then be able to calculate what the velocity would be and how much fuel I'd have to burn to change the velocity of my rocket so I can put it at a different position in a gravitational field. And I'm going to put some videos on our Google Doc that they're a little long and a little bit involved, but if you're interested, you can see exactly what NASA scientists are thinking when they're trying to program a space probe to move from one place to another, or to put it in orbit and create a satellite that can communicate with us. Okay, so in the next episode, I'm going to give you some problems. We're going to solve some problems together using total energy and talking about orbits. And then we're going to move on to escape velocity. All right, good luck.